For this lesson, we're going to be continuing our look at quadratic relations, and we're going to be looking at what are known as transformations of quadratic relations. Specifically, we're going to look at how these transformations affect, to some extent, the table of values, but mostly we're going to be looking at how we transform the graphs. In this first lesson on transformations, we're going to be looking at reflections and stretches of quadratic relations. And I think I'm actually going to start with stretches, and then we'll get to reflections shortly. So the way we're going to start this is I'm going to start off with the parent function. And the parent function for any kind of relation is the simplest version of that relationship. So in the case of a quadratic, the simplest version is the equation y equals x squared. So this is known as the parent. So this is our reference when we talk about the graph. This is our reference graph. It's pretty simple to create a table of values for this. You can see I've got my x values here for the independent variable from -2 to +2. And so if I square each of those, -2 squared, that's equal to 4. -1 all squared, that's equal to 1. 0 squared is simply 0. 1 squared is equal to 1. And 2 squared is equal to 4. So if we graph this, then we have a point here at 0, 0. We have a point at 1, 1. We have a point at 2, 4. And because of symmetry, it's not surprising that when we go to -1, we also go up to +1. These 2 points are symmetric. And when we go to -2, we end up at +2. In this case, the axis of symmetry is along the y-axis, so we're symmetric about that. This is going to be tough to do on the tablet, so I hope you'll forgive me. Try to draw a smooth curve for the parabola. That's not too bad. Okay, so this is y equals x squared. Now the other idea I want to introduce as part of this lesson is the idea of step pattern. You can see I'm asking about that down here. I say, well, what is the step pattern? So the way that you do a step pattern is you start at the vertex, and usually I start going to the right. It doesn't actually matter going right or left, but it is important that you start at the vertex, and then what you're doing essentially is you're taking steps to the right by 1, and then finding out how big a step up do you have to take. So this is my first step. I go right by 1, and I go up by 1. So my first step is 1. When we talk about the step patterns are the changes in the y direction. The changes in the x direction are always going to be 1 for our step pattern. So this is a change in the y direction. Maybe let me write that a slightly different way. So with my step pattern, my delta x's are always 1, and my delta y values are going to be 1. That's the first one. And then I take another step over by 1, and now my step to the next point is 1, 2, 3. So 3 is the next step, and then step over by 1. I didn't actually complete this graph to go far enough, but if I did, let's just add a point in here. It's easy enough to do. If I put a 3 here, then we get 3 squared, and that's equal to 9. 9 is going to be a stretch to fit on my graph, but if we imagine, if we stretch it a little bit, there's a 9. So there's the point. So this will continue up to there. And really, what I'm actually interested in, though, is this step all the way up to here. That's 1, 2, 3, 4, 5. So my next step is 5. And you can probably see the pattern forming here, 1, 3, 5, and the next one's going to be 7, and the next one's going to be 9, and so on. And that step pattern works going the other direction as well. I go left by 1 and up by 1. There's that first one. And then I go left by 1 and then up by 1, 2, 3. That's the second one. And then I would go left by 1 and up by 1, 2, 3, 4, and it's not quite on my scale, but 5, and that would be my next point. So if you know where the vertex is for any parabola, the step pattern is actually a very convenient, a very quick and easy way for us to be able to graph it. Now in this case, we've used the step pattern to graph the parent function, but please keep in mind that the other main point of today's lesson is we're going to be looking at stretching and reflecting. So that's going to have impacts on the graph, which means it's going to have impacts on the step pattern. So let's move on and take a look at some of those impacts. So now I'm going to take a look at the parent function, y equals x squared, and then I'm going to compare that to a couple of transformed functions, 2x squared and 1/2 x squared. So the standard table of values here, we had most of it in our previous note, but -3 all squared becomes +9, +4, +1, 0, 1, 4, and 9. Now 2x squared is literally that. It is, instead of x squared, which was here, I'm going to put in 2x squared. But just to show it genuinely, I could also say that this is 2 times -3 all squared. But -3 all squared is +9, which we had here, and multiply that by 2 and we end up with 18. 2 times -2 all squared. -2 all squared is 4, and double that is 8. So hopefully you can see that all I'm actually doing here is doubling the values from the parent function. 2 times 1 is 2. 2 times 0 is still 0. 2 times 1 is 2. 2 times 4 is 8. 2 times 9 is 18. Similarly, this time I have this multiplying factor of 1/2. So I can take -3. Oh, let me just erase that. I can do 1/2 of -3 all squared. Well, that's 1/2 of 9, which is the same as 9/2, or you could write that as the non-repeating decimal of 4.5, whichever you're more comfortable with. Well, 4.5 is half of 9. If I do the next one, it's going to be half of 4, so it's going to be 1/2 of -2 all squared, which is 4/2, but that's simply equal to 2. That's half of this value. Half of this one is 1/2, which is the same as 0.5. 1/2 of 0 is just 0. 1/2 of 1 is 1/2, which is the same as 0.5. 1/2 of 4 is 2. And 1/2 of 9 is 9/2, which is the same as 4.5. So we've created tables of values for the parent function, or recreated the parent function. And then if I take the parent function and multiply by 2, it doubles my values. If I take the parent function and multiply by 1/2, it gives me half of the values. And these are the y values. Notice the x values haven't changed at all. We use the same set of x values in each case. So this one, what do we notice? Well, here we're simply doubling. So I'm doubling my y value from before. So I'm doubling the parent, let's say. And here I'm halving HAL. Which means I'm cutting the parent in half, or I'm dividing the parent by 2. Okay, so let's see what these actually look like. What does it mean when you double the parent function, when you halve the parent function? And then we're going to take a look at the step pattern. So I'll use blue to do my parent function. So 0, 0. And I'm actually going to use the parent function step pattern here. So over 1, up 1, over 1, up 1, 2, 3. And that matches my table of values. I've done this table value enough times that I'm pretty familiar with it. And then by symmetry, over 2, and so you can use symmetry or the step pattern at this point. And again, it's a bit of a chore to try to do this with the tablet, but let's see if I can't at least not do a terrible job. That right side is not great, but hopefully you can forgive me. Okay, so we did this one in blue. Let's do this one in red. So if we think back, we had the starting point at 0, 0. If you want to switch back, I'll just bring that up again. So we had 0, and then going away we had 2, 8, and 18. So over 1, and this time it was to 2. At x equals 2, it was at 8, and I'm obviously not even going to be able to get close to 18. At negative 1, it's equal to 2. At negative 2, it's equal to 8. Now this one's going to be even more difficult to do in any reasonable way. That looks terrible. And that's even worse. Hold on a second. That's not too bad. Okay, so this one, I'll actually label it here. This is y equals 2x squared. The first one was y equals x squared. And the last one I'll do in green, and that was 1/2. So when x equals negative 3, we're at 4.5, then 2, then 0.5, then 0. So negative 3 is at 4.5, 4.5. Negative 2 is at positive 2. Negative 1 is at positive 1/2. 0 is at 0. Positive 1 is at positive 1/2. Positive 2 is at positive 2. Positive 3 is at 4.5. And try to do a smooth curve. Y equals 1/2 x squared. So what do we notice about our step patterns? Well, let's have the parent function. So this is y equals x squared. The parent function for that one is over 1 up 1. From there, the step pattern is always continuing from the next point. So over 1, starting at the vertex, over 1 up 1. That's the first step. From that first point, we're not on the x-axis anymore. We're actually above it. Over 1 up 1, 2, 3. From this point, it would be over 1 up 1, 2, 3, 4, 5. We didn't get there, but that would be the next one. This one is increasing by 2 each time, and so on. For y equals 2x squared, in the same way that the y values just changed in the y coordinates, the step actually changes as well. But let's confirm that. Let's take a look. Starting at the vertex, over 1, up 2. From that point, over 1, up 1, 2, 3, 4, 5, 6. See how that's doubled? So 1 became 2. 3 became 6. 5 is going to become 10. 7 is going to become 14, and so on. So by having this factor of 2 in front, this multiplier of 2, I have doubled the size of my step pattern. And that is the introduction to this idea of a transformation, of a stretch. I've taken this blue parent function and I have stretched it out vertically. I've made it taller and thinner. It's like I grabbed it by a pair of handles and pulled upwards on it. Let's finally finish with y equals 1/2 x squared. So what's the step pattern look like for that one? I went over by 1, up by 1/2. Now this is where it's easy to go wrong. From this point, I go over by 1, and now let's count out how many halves I have to go up, because this one was by 1/2, so that's 1/2, 2 halves, 3 halves. And then from here, I go over 1, 1/2, 2 halves, 3 halves, 4 halves, 5 halves. And the reason I wanted to do it that way, and obviously the next one would be 7 halves, etc., because the step pattern in the fraction 1, 3, 5, 7 is exactly the same, except for now I have divided by 2 or multiplied by 1/2 each time. So there are the step patterns we get. So not only do these transformations affect the graphs, but these transformations affect the step patterns, which means if you apply the transformation to the step pattern, you have a quick and easy way to be able to draw the transformed graph. Okay, now let's take a look at this idea of reflection. Here is my parent function, y equals x squared. The number in front of that is a 1. We don't normally write it. This is y equals 1x squared. And that value in front of the x squared, we call that the a term. If you think back to the standard form of a parabola, y equals ax squared plus bx plus c, that a is the same as what's in front of each of those. In this case, I have a negative sign in front, but that's a negative in front of the 1 that we don't write in front of the x squared. And the way that that affects things is we've looked in the past about the idea of parabola openings. So we said that if the a value is positive, the parabola opens up. If the a value is negative, the parabola opens down. But when we talk about these things in terms of transformations, changing from opening up to opening down is known as a vertical reflection. So when we look at A tells us the direction of opening. The sign of A tells us the direction of opening, and the way we refer to that is whether or not it's been reflected. So if A is negative, then a vertical reflection has taken place. As we saw with our previous examples, the number that is A also has an impact. That was how we got those stretches taking place. And so that's what I'm talking about here. So if we have a number that's not 1 or negative 1, if it's simply 1 or negative 1, that's just a reflection. Negative 1 is a reflection, 1 is the parent function. If we have some other number, we have what's known as vertical scaling. And when we talk about vertical scaling, we actually only care about how much it's been scaled vertically. The word reflection takes care of the plus or minus part, specifically the minus. So when we talk about vertical scaling, we really ignore the minus, and all we do is focus on how big is A. In mathematics, this is known as the magnitude of A. That's basically saying, look, don't bother me with the sign of A. I've got something else to deal with that. Just tell me, how big is A? Is it a big number or is it a small number? And so in language, we call that the magnitude. In mathematics, we have an operation, which is these two vertical bars on either side, and that's called the absolute value. So that takes any number, whether it's positive or negative, and turns it into a positive, so that we're focusing on the positive part. So what we're basically saying here is when I change the number into a positive, no matter what it is, when I change it into a positive, if it's bigger than 1, that means we end up with something that's taller and thinner. So the example that we had in our previous notes was y equals, I don't think it was 3, I think it was actually 2x squared, wasn't it? 2x squared. But another example would be y equals 10x squared. Yet another example might be y equals negative 5x squared. Or y equals negative 1.01 x squared. And that's the most subtle one of them all. First of all, whether it's positive or negative doesn't matter. And take a look, 1.01, when I get rid of that sign, the number 1.01 is a little bit bigger than 1. So this would be a stretch. Not much of a stretch, but it's a stretch. 10, on the other hand, is a pretty significant stretch. These negatives also indicate reflections, and you can see when we talk about reflection versus talking about stretch, we talk about those two things independently. The opposite of a stretch is known as a compression, and that occurs when the number in front is between 0 and 1, when the magnitude of the number in front is between 0 and 1. Negative signs mean a reflection, but we only care about the magnitude when we're talking about the vertical scaling. So what are some examples of this? Well, we did one already, and that was y equals 1/2 x squared. Another example of this might be y equals negative 2/3 x squared. Now beware, it's not as if every fraction will work, because if I put y equals 5/4 x squared, well, 5 over 4 is actually 1.25 x squared. This belongs up here, so this is absolutely not correct. And you could also have decimals, of course. Y equals 0.2 x squared. So anything positive or negative where this value of a is between 0 and 1, or the magnitude of a, that's a vertical compression. Okay, so now classify these. Starting with y equals x squared, the parent function, what would you say has happened when I have 1/4 x squared? Well, there's no negative sign, so we don't have to worry about a reflection. And so the only transformation here is a vertical. Now, what is this going to be? 1/4. That means that's a compression by, now typically, I would say this is a vertical compression by 4. But that can be confusing for some students. It is also acceptable to say that is a vertical compression by 1/4. Some people find that more straightforward. The key I want to emphasize here is you must recognize that that is a compression. You must use the right word here. But as far as the quantity goes, if you say a vertical compression by 4, you're saying that this thing has been shrunk by a factor of 4. If you say vertical compression by 1/4, because you've used the word compression, the person listening to you should know what you mean. So both of these are correct in my books. Let's take a look at this other one, y equals negative 3x squared. Well, this one actually has two transformations, so we need to list them in order. And when we talk about them in order, normally for just multiplying, we just go from left to right. So this one has a vertical reflection. And the second transformation, the absolute value of negative 3 is equal to 3. That's what it means to take the magnitude. So this is obviously a number bigger than, in this case, the absolute value of a is bigger than 1. So this is a stretch. So this is a vertical stretch by, and how much is it a stretch by? It is a stretch by 3. And that's it for this one. Just to make that clear, here you could use a 4 or a 1/4. In this case, if you said a vertical stretch by 1/3, that is never correct. Okay? So it is only with compression that I'm willing to give some latitude here. With vertical stretches, a vertical stretch is always by a number bigger than 1. So this is never going to be correct. Even if you said the word stretch correctly, if you say by 1/3, it becomes wrong. Okay, so what we want to do now is let's apply some of these ideas using step patterns and see if we can graph things quite easily. So first of all, y equals x squared. The step pattern for that is 1, 3, 5, and so on. And that's going to start at the vertex at 0, 0, over 1, up 1, over 1, up 1, 2, 3, over 1, and it's off my graph, so I don't have to continue. Left 1 and up 1, left 1 and up 1, 2, 3, and I'm off my graph, so I don't have to continue. And try to draw a nice smooth curve. Caught the edge of the tablet there with my hand. That'll have to do. So this is y equals x squared. Now let's see what is going to happen to my step pattern when I do negative 0.5 x squared. And you know what might be useful here is let's look at the transformations. So this has a vertical, and quite often I'll condense vertical to be just a V. We do need to say vertical though. You might guess eventually we're going to be looking at horizontal, so we need to distinguish between those. So this one has a vertical reflection, and I'll quite often just say reflect as opposed to reflection. And what else are we going to do? We are going to vertically compress by, and you might say by 0.5, or you might say by a half, or you might say by 2. I would accept all of those because it's a compression. But more importantly, let's see what that does to the step pattern. So what's going to happen to the number 1 in the step? It's reflected, which means it's going to become negative, and it's compressed by a half, so it's going to become negative 1/2. What happens to the number 3? It's going to be reflected, so it's going to become negative, and it's going to be compressed by a factor of a half, so 3 is going to become negative 3/2. And then you can probably see the pattern start to form: negative 5/2, negative 7/2. So let's see how those graph. We start at 0, 0. We go over 1, down a half, so that takes us to here. Now, this is 3/2, so it might make sense to count by halves here. So I'm going to go over 1, and then I'll go down 1/2, 2/2, 3/2. Let me actually put dots there to indicate I'm over 1, and then from here down 1/2, 2/2, 3/2, and there is my next point. And let's see, can we fit 5/2 on this graph? Doesn't look like it. Over 1, down 1/2, 2/2, 3/2, 4/2, 5/2. So the point would be around there. Now I'm just going to take away these scribbles. They certainly don't add anything to the overall look. And I'm going to do the same thing on the other side. Left 1, down 1/2. Left 1, down 1, 2, 3/2. If you don't want to count them out, you can also use symmetry. You know it's going to be at the same level. Counting it out on both sides might be a good way to check to make sure you've done it correctly on both sides. And then left and then down 1, 2, 3, 4, 5/2, which is about there.